Let's see the fourth example on the concept of vector fields. So it says let v1 is equal to u1 x minus u3, v2 is equal to u2, and v3 equal to x u1 plus u3. So we have two sections here. First one says prove that the vectors v1 of p, v2 of p and v3 of p are linearly independent. At each point of v3. The second question is express the vector field x u1 plus y u2 plus z u3 as a linear combination of the vector fields v1, v2 and v3. So first we look into the first one, afterwards we will see the second. For the solution of A, since we have the vector fields v1 is equal to u1 x minus u3, v2 is equal to u2, v3 is equal to x u1 plus u3. Now we have to prove v1, v2, v3 are linearly independent. So first we will write it for the arbitrary point p. v1 of p is equal to u1 of p plus 0 into u2 of p. I can write like this, minus x u3 of p minus x of p into u3 of p. So v2 of p is equal to 0 into u1 of p plus 1 into u2 of p plus 0 into u3 of p. v3 is equal to x of p into u1 of p, because we are finding at the point p, plus 0 into u2 of p plus 1 into u3 of p. So they can be rewritten as v1 of p is equal to u1 of p plus 0 into u2 of p minus p1 into u3 of p. v2 of p is equal to 0 into u1 of p plus 1 into u2 of p plus 0 into u3 of p. v3 of p is equal to p1 into u1 of p plus 0 into u2 of p plus 1 into u3 of p. Because x, y, z are natural coordinate functions, therefore x of p is equal to p1, y of p is equal to p2, z of p is equal to p3, where p is given by order triplet p1, p2, p3. Now to check whether v1, v2 and v3 are linearly independent, we will consider a matrix corresponding to the coefficients of u1, u2 and u3, and we have to find the determinant. If the determinant is non-zero, then they are linearly independent. If the determinant is 0, they are linearly dependent. Now the determinant to be found, that is 1, 0 minus p1, 0, 1, 0, p1, 0, 1. So it is equal to 1 plus p1 square. So for any p, this will never be equal to 0 for all point p. Hence this implies v1, v2 and v3 at the point p for any arbitrary p are linearly independent. This is all about the question asked in section A of the exercise 4. Now coming to B. So they are asked to find xu1, yu2, zu3 as a linear combination of v1, v2 and v3. First we have to consider we have v1 as u1 x minus u3, v2 as u2, and v3 as x u1 plus u3. So what we need is we have to find x u1 plus y u2 plus z u3 as a linear combination of v1, v2, v3. So therefore we have to express u1, u2 and u3 in terms of v1, v2 and v3. So from the second equation we have directly have v2 is equal to u2 is equal to v2. So from the first one we have u1 is equal to v1 plus x u3, and from the third u3 is equal to v3 minus x u1, v3 minus x u1. So I will just put u3 in this equation. So u1 is equal to v1 plus x into v3 minus x u1. So this is equal to v1 plus x v3 minus x square u1. So taking u1 on the left hand side, 1 plus x square v1 plus x v3. So therefore u1 is equal to v1 plus x v3 by 1 plus x square. So we have u2. Now we have to go for u3. u3 is equal to v3 minus x u1. u1 means v1 plus x v3 by 1 plus x square. v3 minus x v1 by 1 plus x square minus x square v3 by 1 plus x square. So taking v3 on the same, 1 minus x square by 1 plus x square minus x v1 by 1 plus x square. This is equal to v3 1 by 1 plus x square minus x v1 by 1 plus x square. So this is u3. So we have u1, u2 and u3. So just we will put the values of u1, u2 and u3 in the equation. X u1 plus y u2 plus z u3. So this is equal to x into u1 means v1 plus x v3 by 1 plus x square, y u2 means plus y into u2 means v2 plus z into v3 by 1 plus x square minus x v1 by 1 plus x square. So this is equal to x v1 by 1 plus x square plus x square v3 by 1 plus x square plus y v2 plus z by 1 plus x square v3 minus xz v1 by 1 plus x square. So taking v1 together, v2 and v3 separately. So this is v1 x by 1 plus x square minus xz by 1 plus x square plus y v2 plus v3 into x square by 1 plus x square plus z by 1 plus x square. So this is equal to x by 1 plus x square into 1 minus z v1 plus y v2 plus 1 by x square plus z by 1 plus x square v3. So therefore x1, y2 and z3 can be expressed as linear combination of v1, v2 and e3 with the coordinates. For v1 as x of 1 minus z divided by 1 plus x square. For v2 it is y. For v3 it is x square plus z by 1 plus x square. So this is how this is all about exercise 4. We'll meet in the next exercise. Keep watching. Thank you.